All right, our second day of review. And if you can look at the title of your review sheet, we are going to cover a lot and kind of jump around to a bunch of different things. We're covering basically functions, dot, dot, dot. And so that'll include some absolute value, include some radical, some piecewise, some inverse, and rational. We're going to buzz through it, just hitting the key skills. And then after the review sheet, there will be a chance to practice some key test problems. Just like yesterday, make sure you have the NC Desmos or NC Test version of Desmos. Remember to just kind of Google NC Test Desmos to get that pulled up. If you hit that first link, you will get access to it. And that'll just make sure that you have all the ability you have when you take the test. So, first things first, solving equations with absolute value. We should be able to solve all of these graphically, which we'll do in a second here. But we're going to run through how we solve them algebraically first. With absolute value, first we want to isolate the absolute value. Then we're going to set equal to the positive and negative version. After that, we're going to solve like normal. So if we kind of remember this absolute value sign here, these bars outside are x minus 4, they are going to mean that we kind of split our equation into two. We have x minus 4 equals positive 1. And we also have this world where x minus 4 can equal the negative version as well, because anything that gets evaluated in that absolute value will turn out to be positive. So if we set that up and then solve both sides of our equation, or both of our equations here, adding 4 on both sides for our left side, we get x equals 5. And adding 4 to both sides for our second equation, we get the option of x equals positive 3. These are our two options here. Now, if you were to kind of go through graphically, like we did the other day, I'm going to kind of jump ahead and we're going to do these one by one as opposed to doing them all after the fact. We plug each side of the equation into Desmos as separate functions. We locate the intersections, and the solutions are x values. So let's go up. Let's check this out. On the left side, we're going to have x minus 4, absolute value of x minus 4. So if you need that, what you want to do is go into Desmos, click your keyboard, and we will hit the absolute value sign, x minus 4, and that is equal to 1 as a new function. Notice how we're going to have to set it as f of x equals 1 for that portion. And we have two intersections here. One of them's at 3, one of them's at 5. If I check my work here, one of our answers was at 3, one of our answers was at 5, so we're good to go. Next, for example 2, this is where step 1 comes into play. We need to isolate the absolute value first. We have this 4 on the left here that we need to divide out from both sides before we can do anything with our equation. So we divide out the 4 from both sides, get absolute value of x minus 3 equals 3, and then that's where we can split into our two equations here. X minus 3 equals positive 3, and x minus 3 equals negative 3. Then we go through, we add 3 to both sides. We can do this in both equations if we want to work them at the same time. We get x equals 6. And in our other equation, add 3 to both sides. We get x equals 0. So let's test this out graphically. In our first equation, this will be 4 times on the outside times x minus 3. And our second equation is going to be 12. And again, the 12 won't show up, so we either need to throw y equals out in front of it, x equals out in front of it, or the f of x notation. And if we do that, we'll see that we have an intersection at x equals 0. We also have an intersection at 6, so that works there. Matches our previous work. Now, solving equations with radicals, this first step, isolating the radical, applies as well. But then to undo our radical, we're going to raise both sides by the second power. So here's what this looks like. In our first example, we actually don't have we already have this thing isolated. So I'm going to rewrite this step here real quick. Square root of x minus 3 equals 5. And what I'm going to do is I'm going to raise both sides by the second power because that undoes our radical sign. We're square rooting on the left, so we want to square it and square it. That square undoes that radical sign on the left, so we're just left over with x minus 3. 5 squared is simply 25. And then we can solve the rest of our equation, right? X minus 3 is to get rid of that 3 and move it over. We add it to both sides, and we get x equals 28. Let's try this out in our Desmos here. So if I kind of get rid of my equations, have two new ones, we had the square root. So let's see if I can type this in correctly. Square root of x minus 3. And notice how I can't just type in equals 5, right? That doesn't work. We need to actually type the 5 in as a new equation. So we'll go f of x equals 5. And if I look here, it's going to take me a while to hunt and find this, but if I look for my intersection over on the right, we'll find one. Finally, we get an answer of x equals 28, which matches our work in here. Okay, similarly to our absolute values, let's do an example where we have to isolate that radical first in example 4. Again, we're being multiplied by this 4 out in front, so we want to divide by 4 on both sides. We do that, we get the square root of x plus 2 equals 12 divided by 4 is 3. Then we want to take the radical of both sides, or get rid of the radical of both sides. So I'm going to square both sides here. The x plus 2 square root squared cancels that out, so we're just left with x plus 2. The 3 squared gives me 9. Then I can subtract 2 from both sides and get an x value of 7. Again, this is something that we can much more easily do graphically. So let's try this out. If we get 4, let's change the screen equation. We get 4 times the square root of x plus 2, and we want to set that equal to 12. I'm going to go back and home my graph in. I'm going to kind of have to scroll up to find the intersection here, and it looks like we have an intersection at x equals 7, so confirmed that that's my answer. Again, solve graphically. It's going to be easier, but make sure you understand the process for solving these algebraically. One quick final note. With radicals, keep in mind that they can show up as fraction exponents as well. So this expression here, 4 times x plus 2 to the 1/2 power equals 12. That's the same exact thing as this expression here, 4 square root of x plus 2 equals 12. We already kind of worked through solving graphically for these, so we can move on to piecewise functions. This is something that we covered briefly over just a couple of days. They are built up from multiple subfunctions that are going to vary based on the input. And when I say the input, I'm talking about x usually. So in example 5, we have 3 different subfunctions. This x to the third, or x to the third minus 7x, this 8, and this square root of 2x plus 3. Depending on what our x value is, we're going to pick one of those to evaluate our function. So if we're evaluating when x equals 11, that x equals 11 is greater than 3. So we are going to use this function to evaluate it. We'll have f, our function at 11, equals the square root of 2 times 11 plus 3. That is equal to the square root of, 22 plus 3, so 25, which is equal to a value of 5. Okay, if we're trying to evaluate when f equals 2, well, in this case, that would fall into this middle function range, right? F of 2 is between -3 and 3, so we would plug in f of 2 equals what our function is, and in this case it's just 8, so we can leave it exactly as 8. For all those values in between, we are going to have 8. Now, there's going to be some problems that we need to graph piecewise functions for. So we can do this using these kind of squiggly brackets here. For example, 5, it's going to look like this. The orange part is graphed in one line, the yellow part is graphed in another line, and the green part is graphed in that last line here. So let's go ahead and do that. Make sure that you have the ability to do that here. Go x to the third minus 7x, and here's my squiggly brackets. Let's double check what we're typing in. We have x is less than or equal to -3. And we can see how that starts to populate on my graph, right? I have a function or a line here, and it gets cut off at a certain point, specifically -3. Let's keep going. The next portion of my function is 8. And that's going to happen from -3 is less than x is less than or equal to +3. So if I do that here and kind of zoom out until I see my graph, notice how this red line just popped up. So we had our first piece of the function, the second piece of the function is there. And finally, that green portion, square root of 2x plus 3. So I'm going to type in the square root of 2x plus 3. Use my squiggly brackets to kind of define that domain. And that's going to happen where x is greater than 3. And notice how if I get rid of that real quick, my graph goes on past that point. That squiggly bracket with x is greater than 3 is kind of what cuts off the graph and turns it into a piecewise function. All right, moving on to something called inverse functions. Inverse functions can really be applied anywhere. We mainly saw them in the context of what we just talked about, but this can apply to exponentials, logarithms, polynomials, anything. Whenever we want to find inverse functions, we want to undo all the operations of the original function. Here's the steps we went through to do that. First thing we did was help get rid of our notation. Okay, we just changed f of x to y. Then we swapped x and y. There's a reason I have these bolded. It's the most important step. It's the crucial understanding of what an inverse function is. It switches around our inputs and our outputs. Then we solve for y, and then we kind of just change our notation at the end, y changing to that inverse notation. So if I kind of work through these steps here in step 1, for example, 6, I'm going to change my f of x to a y equals 3x minus 1, or minus 6. And then this is that crucial step, step 2. I'm going to swap my x and y variables. So x equals 3, y minus 6. Then I'm going to solve for y here. I'll do this step in orange. So we're going to add 6 to both sides, trying to get the y alone. So then we get x plus 6 equals 3y. And then we're going to divide 3 on both sides to get that y alone. So if I scroll down, need a little more space here, we get x plus 6 over 3 is equal to y. And if I want to take that final step there, swapping out the y to the f inverse, that's where I would want to do x plus 6 over -3. And I'm actually going to write that as f to the -1 x on the left side here. So let's try that again with example 7. We got a little funkier thing to work with here. Started off the same way. Get rid of that y, 2x squared minus 3. Swap out the x and y. So x is equal to 2y squared minus 3. Then I'm going to kind of start moving stuff over. So plus 3 on both sides, trying to get that y alone. X plus 3 equals 2y squared. Okay, then we want to divide by 2 on both sides. So x plus 3 divided by 2 equals y squared. And finally, to get rid of this exponent here, to get rid of the square, we want to square root everything. All right, so we're going to square root everything. And this is a tricky component. When we square root stuff, we want to make sure we account for the plus or minus on both sides of that thing. So plus or minus the square root of x plus 3 over 2 equals y. The square and the square root cancel out. And so I'll just rewrite this with our new notation. This time our function was h. So let's write it as h inverse of x equals plus or minus the square root of x plus 3 over 2. All right, last one here. This one's dealing with a square root that we're going to have to undo by squaring both sides of the equation, similar to how we were solving our radicals earlier. So we're going to start by changing our g of x to y equals 2 times square root of x minus 1. Then we can flip the location. X equals y. Oh, sorry. X equals 2 times the square root of y minus 1. Then we're going to divide on both sides. Got to isolate that variable first. So we get x over 2 equals the square root of y minus 1. And this is where we can take the square of both sides. This is a very funky problem, but good exposure here. X squared over 4 equals y minus 1. And so finally, to get this all by itself, we add 1 to both sides. And we'll get this kind of nasty formula here. X squared over 4 plus 1 equals y. In which case we can just write as one more step here, the inverse of g is equal to x squared over 4 plus 1. Now, the last kind of comment about inverse functions is dealing about when they are graphed. So when they are graphed, we still want to flip that x and the y, and that shows up by reflecting across the diagonal line y equals x. Let's see what I'm talking about here in example 9. So if f of x equals x squared, then what does the inverse graph look like? Let's check this out with Desmos. So if f of x is equal to x squared, okay, that is what our base graph looks like. All right. We are going to reflect over this diagonal line, this red line here that I make a dashed. That is going to reflect over. So it's not going to look like that. It's not going to look like this where it mirrors over the y-axis. It is going to mirror over our diagonal line here. So it'll look something like this and like this. Let's see how close I got. One trick we can do is we can swap out this f of x. We can call that x. And we can swap out the x in our equation. We can swap out with y. And we can get a good view of what that inverse looks like. And my bowing might be a little off here and there. But generally, pretty good idea of what that inverse looks like. So if I wanted to sketch this on my sheet, I would have a inverse sketch that looks like that. All right. The last kind of topic we're going to cover on here and the last type of function is a rational function. We're going to buzz through this pretty quick because we covered this more recently. Rational functions are polynomials divided by other polynomials. They're going to have three different types of discontinuity, which we covered before. Horizontal asymptotes. I'm going to make a quick sketch of that in red. That is a horizontal asymptote. Notice how the graph splits there. A vertical asymptote, I'll make in orange. And finally, a point of discontinuity or a hole. Let's kind of signify that in yellow. That will show up there. If you want to label your graph, go ahead and do that. We can find these three different things graphically pretty easily, okay? We can find horizontal asymptotes by testing horizontal lines with y equals something. Vertical, we can test with x equals something, and the holes can be found by kind of creating a table or searching with our cursor. Let's try this out with this example here. Our function is given here. There's a lot going on. Let's plug it into Desmos and see what's actually happening. So I have my function f of x equals, I have some fraction. I always like to make the fraction first. On top we have 4 times x minus 2, and that's times x plus 1. And on bottom we have x minus 2 and x minus 3. So I look at my graph, I might have to zoom out to get a little more clarity. It looks like I have a vertical asymptote here. Notice that gap there. I have a horizontal asymptote here. Let's test both of these things, okay? So it's asking us where's the horizontal asymptote, so I can test that by looking for y equals something. So it looks like maybe that happens at y equals 3. Let's try that out. I look at y equals 3. Notice how there's an intersection here. So that's not going to work. That's a little too low. I'm going to need to move that up. So maybe it's at y equals 4 instead. And indeed, that looks like it doesn't actually hit my graph ever. So we're good with that y equals 4. That vertical asymptote, it looks like it might be at 4 as well. Let's try that out. X equals 4. If I look here and I see, it looks like we do have an intersection up there at 4, so I'm too far to the right. Let's back it off a little bit. X equals 3. If I scroll down a bit and scroll up a bit, it looks like I'm okay. So I'll zoom out. I'll kind of clear some of my sketches here. And I should be good at y equals 4 and x equals 3 for my two asymptotes. So y equals 4, x equals 3. So this final question, is there a hole at 2? This is going to take some searching. If I look here and I go to my graph at 2, which I'm going to need to click and drag, click and drag, click and drag, you'll notice that I can go past 2, so I don't have an asymptote there. But if I hit 2 exactly, notice how it shows up as undefined. I'm going to make my text a little bit bigger here. If I hit 2 exactly, I have undefined, and my graph actually, the cursor starts to have a hole in it that I can visibly see. Another way to do this is if I want to click on my function, click this settings, and create this table. Then I can either look at the x value of 2 or add in the x value of 2, and we'll see that it's undefined there. So that does confirm that we have a hole. So my answer is yes there. All right, a few more things to do. With rational functions, we also worked on multiplying, dividing, and adding, subtracting them. So just a quick review of what's going on there. Multiplying, we go straight across. So all we do is top times top, bottom times bottom. On bottom, we have x plus 8 times x minus 4. On top, we have 3 times 1. If I actually work through that, we get x squared plus 8x minus 4x minus 32. That'll be all over 3. So if I want to simplify that just a little bit further, I'll move to the right a little more. I'm going to actually probably have to clear my selection in a little bit here. A simplified form of that will be 3 over x squared plus 4x minus 32. Okay, if we're dividing, we are going to use that rule, keep, change, flip. Right? That's the big rule for divide. So we keep that first expression, 3 over x plus 8, change division to multiplication, and we are going to flip around that last one, x minus 4 over x minus 3. Then we can multiply straight across, so we get 3 times x minus 4. Notice how I'm throwing parentheses around that. And we get x plus 8 times x minus 3 on bottom. We go ahead and we do that problem. We get 3x minus 12 up top. And on bottom, this is the same. Well, actually, it's a little bit different than before. We should get x squared plus 8x minus 3x is 5x minus 24 on bottom. And finally, this last one, adding, subtracting, we're going to use that butterfly pattern to make our denominators the same. So on bottom, we're just going to go, well, I'll start on top. We have our 3 times x minus 2 plus our 1 times x plus 1. And on bottom there, we're just going to go straight across. We have x plus 1 times x minus 2. Seem a little sloppy with my finger writing there. We go through, we multiply everything. We get 3x minus 6 plus x plus 1 all over. Now we get x squared plus 1x minus 2x minus 2. And so if we fully simplified that out, on bottom we'd have x squared minus x minus 2. And on top we'd have 4x minus 5. All right, very last thing we're going to do today is solving rational equations. It's kind of starting or ending the way that we started. We are going to start, though, with graphing, okay? I always recommend graphing, and then we'll kind of figure out the manual process, the algebra process for this. If we're given this equation, 3 over x plus 2 equals 4 over 2x minus 1, we can solve that by graphing the same way we did on page 1. So the left side of our equation, let me clear out my work in Desmos here. The left side of our equation is one graph, 3 over x plus 2. The right side of our equation is our other graph, 4 over 2x minus 1. Let me just double check everything's good. And I'm just going to basically look for our intersections. It looks like they might intersect as I move to the left here. If I look, it actually looks like we never do, which is good to know. So that doesn't happen. I'm going to come back to the middle here. And it doesn't look like they converge as I go up, but as I go right, looks like we do converge here. And we have an intersection at x equals 5.5. So if I'm going to mark up my notes, I'm going to say, hey, this is graph 1 on the left, graph 1. This is graph 2 on the right, and we find that intersection at x value, and we get x equals 5.5. Now, if we want to solve this algebraically, the first thing we want to do is cross multiply to eliminate all of our denominators. So to do that, let's look through this step here. Here's our cross multiply number 1. So we have 3 times 2x minus 1. Notice the use of parentheses there. That's going to be equal to my second cross multiply step, 4 times x plus 2. I'm going to go ahead and simplify those expressions first and kind of see where it gets me. We get 6x minus 3 equals 4x plus 8. And then I'm just solving for x here. I need to move everything over to all the variables over to one side. I'm going to move the 4x over to the left. That gets me 2x minus 3 equals 8. And I'm going to move that 3 over to the right, adding 3, adding 3. So I get 2x equals 11. And then finally, to get that x all by itself, oops, I just lost the steps here. Hold on. All right, I think I got everything back here. So we have 2x equals 11. So we need to divide by 2 to finish out this problem. And we get x equals 5.5, which was the same thing that we had over when we solved it graphically as well.